think people are still coming in, but we probably should go ahead and get started. Hi, everyone. My name is Carolyn Halpern. Welcome to the session on guidelines for analysis of ad health data. We have two presentations today, and just to give you a little more information about the logistics. So I will introduce the speakers before their presentation. If you could remain muted if you're not actually presenting, and please enter your questions into the chat. And after the two presentations are over, I'll work through the questions in the chat for the presenters, and then we should have 30 minutes for questions after the two presentations. So there should be plenty of time to answer all the questions that you have. So let's see. So our first speaker today is Kathleen Mullen-Harris from UNC-Chapel Hill. If you were in the plenary, you know that Dr. Harris was the Ad Health Director from 2004 to 2021, and she is an Ad Health Parent Study co-PI. So she will be presenting on correcting for design effects and selecting weights. I'll turn it over to you, Kathy.
Okay, let me share my screen, which takes a couple little steps. I sometimes get them in the wrong order. All right.
Well, I never have that problem, Kathy.
Is it coming up? Okay, hold on. All
it's
right.
The notes page.
Yeah, all right. And so I just have to do this. Okay, that should work. Okay.
So we're still seeing the notes page.
What?
There we go. Now it's right.
All right. Thank you. Big delay there. Okay, so I'm going to talk about design effects and selecting weights for some of the more common types of ad health analyses. And this is really just a brief overview. I'm actually filling in for our ad health statistical methodologists. So I'm hoping that I can provide you with the information that you need. And if not, we can always get back to you if there's more details that we can provide. So given that, I just wanted to first point out some resources for you that would be very valuable moving forward and using ad health data. So these actually are about the ad health design. Bob Hummer mentioned this in the plenary. The cohort profile really spells out the design. This is a little shorter sort of published version of this second document here, the ad health study design and accomplishments. That's on our website. And I was actually going to mention in the plenary too that on our website under user guides, we have a large number of user guides. This is the ad health study design and accomplishments is one of our user guides. Actually, and I think the cohort paper is also, the cohort profile is also posted there, but there is another place where you'll find a lot of very useful information about the various types of data in ad health. So those are two good resources. And then these are resources for, some of guidelines for analysis. The first one is by Ping Chen and myself on guidelines for analyzing ad health data. And I'm basically presenting information from this to you today, but it's extremely detailed. There's a large number of examples. There's a large number of, here's common problems and here's how to solve them. So I, highly recommend that you go to this. And then the second is how the grand sample weights were constructed. Okay, so, the aspects of the ad health design that you need to pay attention to in your analysis are three things. The first is stratification by region. The second is clustering of individuals within schools. And the third is unequal probability of sample selection. I'll come back to those, but I wanted to review again the sampling design and, why these are important issues. So, recall that AdHealth used a stratified clustered sampling design from a list of all high schools in the country in 1994-95. That's the school sampling frame, the QED. We selected a stratified sample of schools, and it was stratified by size of school, school type, location, urban, rural, suburban, percent white, and region. So we had 5 levels of strata, the region being the largest. And then of course we selected a feeder school and so on. And we end up with 80 schools and 80 different communities. But then when we selected the individual adolescents, we used the school rosters that were given to us. And then we selected adolescents from these school rosters. And I think I mentioned this in the plenary. We have this main sample or core sample where we selected 200 students from each of these pairs of schools. And this sample here is actually self-weighted. I mean, because this is nationally representative sample of schools in the United States in 1994-95, and then these are students from those schools. So the point is that these students, these 200, they know each other. They're in the same schools. So they are clustered together. And that affects analysis when you're analyzing the adolescents by themselves. And I'll come back to that. The other aspect of the sampling design is we had a number of oversamples. We oversampled a high education Black sample. These are African-American students adolescents who's had one parent, had at least one parent with a college degree. We oversampled Puerto Rican adolescents, Chinese adolescents, and Cuban adolescents. These are our ethnic samples. We oversampled adolescents with a disability, primarily a physical disability, and so on. We oversampled genetic samples, identical twins, half sibs in the same family. Okay, so there was differential probability of selection. All right, so returning then, of course, then the things that we're going to need to adjust for here is stratification by region, the clustering of individuals within schools. The reason that this is problematic is that statistical theory requires that our unit of observation are independent. Well, adolescents within the same school are not independent of each other, and in fact, the outcomes will be more similar within schools and across schools. And then the last thing is, of course, the unequal probability of sample selection that I just talked about. So unless you use adjustments then for sample selection and participation, the estimates from your analysis can be biased, right? When any factor that's used as a basis for selection as a participant also influences the outcomes of interest. And let me just give you a quick example. Black adolescents whose parents were college graduates were one of the oversamples. So parental education is a very common factor used in our analyses, and it's also a factor that affected selection of Black youth in the AdHealth study. Parental education also affects family income. So unless you use techniques that adjust for sort of the oversampling, an estimate of the income of Blacks will be biased. So, any analysis that includes family income or parental education or other variables actually even related to family income can produce biased estimates unless proper adjustments are made for oversampling. Okay. All right. So now I'm going to talk to you about how to make those adjustments and a failure to account for these sampling design issues, usually leads to underestimating standard errors. This is general. And then, of course, false positive statistical test results. So in this next slide, this sort of describes, how you make these adjustments. So stratification, which, the usual, impact on the analysis after adjustment is made is it reduces variance. And the way you adjust for this is you use a post-stratification variable, and that's the census region. Adjusting for clustering of students, as I said, that will tend to increase the variance after adjustment is made, reducing the false positives. And to adjust for clustering, you simply use the primary sampling unit variable, which is the school identification. And I'll the document, and I'll show you what these variables are. And then unequal probability of selection also tends to increase the variance estimates, but it also can bias a parameter point estimate, and you have to use sampling weights. So now we're going to talk about selection of sampling weights for analysis. And so, the sampling weights were designed to turn the sample of adolescents that we interviewed into the population we want to study. That population are adolescents in grades 7 through 12 in the United States in 1994 and 95. And so by using these sampling weights as well as a variable to identify clustering of adolescents within schools, you can obtain unbiased estimates of population parameters and standard errors from your analysis. Now, the AdHealth sampling weights were developed for analyzing combinations of data from the in-home interview using a variety of techniques. And so I'm going to show you a lot of tables of sampling weights, and they're all going to run together, and you're not going to be able to remember anything, but you'll be very grateful to have them later when you're in your analysis and you're trying to figure out what sampling weight to pick. And so just to define a few terms here, a single level population average model. So these are analyses that provide a population estimate for adolescents enrolled in school for the 1994-95 academic year. And they usually, which is our population, our nationally representative population. And usually, these analyses usually involve sort of fitting a population average, a single sort of level model. And we're typically, users are usually using the individual level data, the respondent level data to estimate models. We also have multi-level models, and I'll show you the weights for these, but I'm not going to go into them in a lot of detail. But these are analysis that are providing estimates for adolescents who were in school during the 1994-95 academic year, but they're designed to estimate a model where the levels of interest in the analysis match the sampling levels of school and adolescents. So you might be interested in adolescents' drinking behavior and how that varies by the school level of prevalence of binge drinking, let's say. That would require a multi-level analysis with multi-level weights. All right, so let's look at these, and this, these represent the cross-sectional grand sample weights. This is the name of the weight that's in the actual data set, and gives you an idea of the N. And so the grand sample weight, the cross-sectional weight for wave 1 would be an analysis where you're interested in something in wave 1, like, actually, I remember one of the more interesting questions that we asked back in 1994, I was just thinking about this today, was whether or not the adolescent had a tattoo. And I don't remember what the prevalence, what the point estimate was of that, but I remember I just reading an article this morning about all the Olympians with tattoos, and I think it's probably a lot more prevalent today than it was back in 1994. But you might want to know what that prevalence was, and to get a nationally representative estimate of that for all adolescents in the population you would use this grand sample weight. Again, if you just wanted to know a point estimate at wave 2, like what was the prevalence of having a tattoo 1 year later, maybe it's increased, you use the grand sample weight, you use the cross-sectional weight at wave 2. And so the sample that, the target population you'll see here is, it's adolescents. It's always the adolescents who were enrolled in grades 7 through 12 during the 1994 academic year. And then in each wave, it represents their movement across the life course. So by wave 3, when you're using a cross-sectional weight, you're talking about adults in 2001 who were enrolled in grades 7 through 12 during the 1994 academic year. But the sample, this is the AdHealth sample that you'd be using, would be a cross-sectional analysis at wave 2 would be wave 1 respondents who were interviewed at wave 2. At wave 3 would be wave 1 respondents who were interviewed at wave 3. I think I just said that wrong for the one before. So, I mean, basically, we know that everybody that we follow up in AdHealth participated in wave 1. So in some respects, it's redundant to keep saying that, but, specifically, that's exactly what we're talking about. So these are the cross-sectional weights. You get an idea of, what they're being used for. All right, now, let me tell you when you should be using them. So, remember that cross-sectional analysis are, questions that are mainly interested in examining association between variables. Often the data for both the predictor variables and the outcome variables are collected at the same point in time in the same wave. So this first example then is Y would be the outcome variable, and that's collected in a particular wave 1, 2, 3, 4, or 5. And the X variable would be a predictor variable that would be collected in the same wave, and that's when you would use a cross-sectional weight. Another time you use a cross-sectional weight, and this might be not what you expect, is when your outcome variables in a particular wave, let's say wave 3, but the predictor variables come from wave 1, 2, and 3. Perhaps you're using parental education from wave 1 and grade, whether or not you repeated a grade in school at wave 2, you would still use the cross-sectional weight for this type of analysis. So you can see that the use of the cross-sectional weight hinges on when the outcome is measured. Okay. So I need to keep, Carolyn, you're going to tell me my time, right?
Yes, you're at 16 minutes now.
Okay. Right. So I've been going a little slow. I might pick it up a little bit just so you understand these tables. All right. And so now we're looking at the longitudinal weights, the longitudinal analysis basically investigates changes in measurements taken on the same respondents over time. That is, the outcome variable is measured multiple times. And so here are the longitudinal weights, this is the sample. So for example, if you were interested in an outcome, or you're interested in analyzing data from wave 3, the sample would be eligible wave 1 respondents who were interviewed at both wave 1 and wave 3. Sorry, wave 2, I'm going to really confuse you. Wave 2 and wave 3, you would use this longitudinal weight. And this would describe the target population. So let's say you're interested in analyzing data, and you're starting with wave 4 data, and you're interested in analyzing data for wave 1 response who were interviewed at waves 3 and 4. Okay. Then you would use this longitudinal weight. And we got around to finally making the names of these weights a little more descriptive, at least for the longitudinal weights. So you can see this would be grand sample weight 1, 3, 4. And then here are sets of 3 longitudinal weights at wave 4. And this is when you're analyzing, again, the outcome is being measured at multiple waves. So let's just say BMI, to give you the example that I had in the plenary. You would use the grand sample weight 1, 2, 3, 4, 5. If you are interested in analyzing BMI as it changes from waves 1, 2, 3, 4, and 5 across all waves. Sometimes we eliminate 2, and that's because in wave 2, we did not follow up the seniors. That was a design-based decision. And so if you analyze longitudinal data that includes wave 2, you tend to lose about a sixth of the sample because you're losing those seniors. So sometimes, since wave 2 was also in adolescence at the same time as wave 1, you can maybe sometimes drop wave 2 from your longitudinal analysis, and then you don't lose those cases. And then here are the longitudinal weights for those who participated in waves 1, 3, 4, and 5. All right, let me keep going. And then if there's questions, I can take them later. Here's when you use the longitudinal weights. When you're using the outcome variable, your Y variable is coming from multiple waves of data. Okay. Now I'm going to show you some additional types of analyses. Sampling weights for time to event, which are often referred to as survival analysis or hazard analyses or event history analysis. And this table shows when the outcome or the event is only measured in one particular wave. So let's, for example, say wave 3. That's the first time we collected data on whether or not you have been arrested. So you might just want to find out, time to event, time to first arrest at wave 3. You would use a grand sample weight. However, most of the time, especially when you're looking at using survival or hazard analysis, you're using all the waves of data and tracking them over time, some event. It could be death, it could be marriage, it could be first pregnancy. And in that case, depending on how many waves of data you use for time to event analyses, you want to use the weight from the wave where they were first observed. This is really the point of first exposure to the risk of the event that you're studying. So it's not surprising that it's, if you're looking at time to event and you're using waves 1 and wave 2, you use the grand sample. This is the cross-sectional weight at wave 1.
10 minutes, Kathy.
Okay, perfect. Let's say you're skipping wave 1, you're just using 2 and 3, you use the grand sample weight. These are the cross-sectional weights at wave 2. And so on. So you use the weight from the first wave in which they were observed to follow, their exposure. All right, so I'm almost through all the weights, almost. All right, I just wanted to point out, the sampling weights for wave 5. These were shown, before, but here's our cross-sectional weight. And then we have a set of 3 longitudinal weights, as I mentioned, depending on the waves of data. And I also want to just point out that we have a bio weight for analysis using the biomarker data. As you recall, that's a subsample of the wave 5 respondents because they had to consent. And so one thing that weights do is they correct for that selection of differences in who consents and who doesn't. And I want to point out one of the things, we get a lot of questions about this with longitudinal analysis. Okay, so longitudinal analysis, we're looking at change in measures over time. The outcome variables measured multiple times, and there's often 2 ways you can organize your data. One is as a stacked file or stacked records, and that's when one record per respondent per time point. So, let's say that you have BMI and it's measured, at all waves. Every time BMI is measured, they would contribute a record to a sample. So somebody who was in all waves would have 5 records. That's a stacked file. When you do that in a longitudinal analysis, like a random effects or a fixed effects model, the weight that you want to apply is you want to give the cross-sectional weight that is specific to each of those waves. So I would be using a cross-sectional weight from each wave 1, 2, 3, 4, and 5 for each of those records. A second way of organizing your data is by combining, the changes in measures over time, like you might be measuring change. And in that case, you use the cross-sectional weight of the most recent wave of measurement. That's a common question we get. Okay, so now I'm going to just quickly, these are, just putting them here for your information. We have a lot of special subsamples in AdHealth, and we've developed weights for them. These are, I mentioned this is the wave 3 romantic partner sample that I mentioned, and which has, 500 dating, 500 cohabiting, 500 married couples. You want to use that weight when you analyze that sample. We have an education sample where we collected the high school transcripts of respondents. They have a special weight. We have some other samples at wave 3, which I also mentioned. We tested for urine and for a number of sexually transmitted infections with that were FDA approved kits. And depending on which of those outcomes you're interested in, you need to use a specific weight for them. Okay. And okay, so I'm going to just sort of wrap up here with a couple very simple examples. So when you prepare your files, you want to first determine the waves of data you're using, exclude the missing cases and sampling weights. You want to specify your design type. The most common is with replacement. The stratum variable that I mentioned is called region, and the cluster variable is the PSU SCID, school ID. It's a very, very simple example. And this, let's say we're interested in the research question, what's the mean number of hours of TV watched during a week among adolescents? So this is coming from wave 1. Here's an example of some SAS syntax and some Stata syntax. And then this is the parameter estimate and standard error to predict the average number of hours TV watched in a week. So you get the exact same point estimate and standard error using that syntax.
5 minutes, Kathy.
Okay, and then here's a second example where we are looking at a regression analysis. The question is the performance on the AdHealth vocabulary test, which is a Peabody, which is a picture vocabulary test in AdHealth, is that test result influenced by an adolescent's age, gender, or time spent watching TV? So here's the syntax, and here's the result. You get the parameter estimates and SAS and Stata, and what you see here is that increasing age lowers the score. Males have higher scores, and TV hours reduce the score. And that's it. So, but I finished within time, and I'm happy to take your questions at any time.
Thank you, Kathy. You did have time to spare. There are several questions in the chat, but I think we'll hold them towards to the end. So we'll switch gears a little bit. And our next speakers are Dan Lau and Brian Burke from RTI International. And they will present on Wave 5 mode effects after transitioning from in-person modules to web mail mixed modules. Oh, mode, I meant, sorry, mixed mode.
Hi, Carolyn. Can everyone hear me?
Yes.
All right. So I'm going to try to get the slides up here and share them. And is that working?
We're seeing the edit mode.
Okay, we had this before. And
You might want to click it again. Click the
But
presenter.
that?
Yeah, try that again. It took me a couple times. There you go.
Now we're seeing the presenter notes.
Yeah.
You can click display settings at the top and then swap with the presenter view.
No, next
Uh,
one.
Over to the right, display settings.
One more. Go over to the right.
Under more?
No, there's right now it looks like you're clicked on show taskbar. Go to display settings right beside it at the very top. You're clicking show taskbar.
I don't see display settings.
Oh, all right. I'll tell you what, I'm going to try to do this here. Although I don't know if it's, yeah, it doesn't give me anything. Carolyn, do you have any control over the display settings there? When I click, it doesn't show me anything.
Not that I can see.
Brian, this is where we were before. I'm not sure why you're not seeing display settings now. It's not hidden behind anything at the top of your screen, is it?
Oh,
Nope. What if I retried it again?
okay.
Sure.
Do you have two screens, Brian?
Nope, it's turned off.
Oh,
Okay, let's see if this will work.
Hey,
hey, perfect.
Is that right?
Yes.
Okay, thank you. Sorry, everybody, for the technological issues here, but I'm Brian Burke. I'm with RTI International, and I was and am the Ad Health Project Director for Waves 3, 4, 5, 6 for the parent study and the SOGI grant, if you've been in the generic plenary session. We're co-presenting. Dr. Dan Laus also will do the second part of this presentation. And we want to acknowledge Paul Beamer as one of our contributors in this session. This actual presentation is in regards to mode effects, came about because in Ad Health Wave 5, we had to transition from in-person to mixed mode surveys. And we're going to present this in two parts. The first part will be me defining the problem and what the design we came out with. And then the second part will be Dan describing the mode effects analysis and the outcomes of that. Okay. In-person interviewing, which Ad Health was in school, from the plenary session, you know that Ad Health was in school or in home for waves 1, 2, 3, and 4. And in-person interviewing has long been considered the gold standard for collecting survey data because it usually has higher response rates in other modes. Historically, when you're looking at doing a survey, you in the past have been looking at doing in-person CAPI mode versus a telephone CADI mode, and the CAPI modes always got higher response rates than the CADI modes. For complex data collection efforts like Ad Health, in-person surveys can also provide more accurate and complete responses than self-administered surveys because the interviewers that are in the home can answer questions, clarify concepts, and also motivate the respondents to complete the questionnaire. The major disadvantage of in-person interviewing is very high cost, and it can be many times greater than self-administration via web or mail. It is also well documented that switching to self-administration often risks increasing non-response and measurement errors that will bias the estimates, particularly estimates of longitudinal change. Over the past 20 years, in-person interviewing costs continued to increase, while the data quality advantages traditionally identified with in-person interviewing have somewhat faded. Contributing to the high costs are the declining response rates in household surveys and the associated greater field effort required to successfully locate, contact, and interview respondents. Also, a drawback of in-person data collection can be that the data timeliness can be adversely affected by the additional required in-person fieldwork effort because it's often protracted, the data collection effort is. There is some evidence that the data quality for in-person surveys may not be superior to well-designed web or mixed mode surveys for many topics areas, and it's conjectured that interviewer effects may be a contributor to the data quality erosion. Wanted to mention a little bit from the plenary sessions and what we've had so far, a little bit of history, but I wanted to show this to define the problem we encountered when planning for wave 5. So at wave 3, which was completed in 2001 and 2002, we had 15,170 completed interviews. 6 years later, wave 4 came about in 2007 and 8. We had 15,701 completed interviews. And then wave 5 was in 2016 through 18, had 12,300 completed interviews. But ad health costs per completed interview comparison was interesting. And this is the definition of our problem in planning wave 5. I mentioned previously the first 4 waves were all in person. Wave 5 had web and self-administration as a predominant mode, and this change was necessary because of the increasing field costs. So from wave 3 to wave 4, and you saw the timeframes in the previous slide, the field cost increased 29%. As we were looking at doing a wave 5, again at those timeframes, if you put it out 29% more, it's the third bar graph here of where we'd roughly be at wave 5. And it became the point that it basically became too expensive to try to contact almost 20,000 people in person when they lived in all 50 states and were geographically spread all over the US. So we put together, which I'll talk more about in a minute, mixed mode design, and the actual cost for wave 4 to wave 5 was a 40% decrease in cost. So it gives you a little idea, and that 40% decrease is from the second bar graph to the third, just to give you a little idea of the change in projected cost. What did we do? Well, for wave 5, we proposed a multi-sample, multi-phase responsive design, and the result of this was reduced costs, improved data quality, and provided for estimation of and adjustment for mode effects in cross-sectional and longitudinal analysis. Kathy's presentation, which I hadn't seen before, already talked about this, but I put a little note in here that both cross-sectional and longitudinal weights were produced for wave 5. And wave 5's responsive design approach consisted of multiple data collection phases completed sequentially over a multiple year time frame. Well, what did that look like? Here's the sample design for wave 5 with the actual completed numbers in it at the end. For wave 5, the full sample was randomly split into 4 subsamples, 1, 2A, 2B, and 3. They were, as mentioned previously, they were fielded approximately sequentially. Sample 1, 2A, and 3 were the mixed mode samples by web mail, and they also had a non-response follow-up that was in person as well. And then sample 2B, which is this area here, if you can see my cursor, was conducted in person, and it was designed to replicate wave 4 protocol to the extent possible. We had 1,102 completes for sample 2B, and for the web mail, we had 9,067 completes. So what you were using for sample 2B in comparison to the web mail was about 12%. We had overall about 26% completed in person, but the sample 2B portion is what we're using to look at what happened. Accounting for mode effects. The evaluations of mode effects may involve the use of parallel surveys And this is sometimes called ringed fencing or benchmarking. In wave 5, sample 2B served as the benchmark sample for assessing mode effects, with traditional in-person interviewing accounting for about 26% of the total completed interviews. And remember, I mentioned earlier, sample 2B was about 12% of that, 12% of the 26%. The multi-sample, multi-phase benchmarked responsive design, that's a mouthful, employed in wave 5 was quite novel at that point in time, and there was very little similarities to it in survey literature. So it was really unique, a unique way to move from in-person data collection to multi-mode. The combination of features implemented in wave 5 for controlling non-response bias and measurement effects also appears to be unique. At this point in time, I'm going to turn it over to Dan, and Dan can talk about the rest of it. But I did want to just mention before I left, if anyone, and I'll put this in chat while Dan's talking, but we published a book chapter in a book called Measurement Error in Longitudinal Data in Oxford University Press. I just received my hard copy last week, and the people, almost everyone associated with it is on this panel right now. Kathy and Carolyn were co-authors along with Dan and I and our contributor, Paul Beamer. And I am going to get out.
Can you see my screen?
Yes.
All right, perfect. Thanks, Brian. So Brian had made a very nice introduction about the motivation and why we are doing the mode effect analysis. So for my part is really to demonstrate how we examined mode effect given the redesign in wave 5 and what the results look like. And I will give a brief summary and what we are going to do in wave 6 to continue this effort. So basically for the mode effect analysis, we used a Markov latent class analysis method in order to decompose the differences and understand the measurement errors and the non-response errors from the mode, from the differences we detected from the mode effect analysis. In order to do that analysis, we needed 2 conditions. As Brian mentioned, the first condition is that we needed to have a benchmark sample. That's why we have the sample 2B in wave 5 as a parallel sample in which we implement the same in-person interviewing methodology as we used in the prior AdHealth waves. Then we used the mixed mode design for the rest of the sample in wave 5. Another condition we needed to do this analysis is that we needed to use data from multiple waves. So the minimum waves we need are 3 waves. That's why we used data from waves 3, 4, and 5 for this analysis. So these are the 2 conditions. So the primary objective for mode effect analysis is help us to evaluate the change in accuracy levels for cross-sectional and longitudinal estimates resulting from the wave 5 redesign. For the data, as I mentioned, is we use the 3 waves of the data. From those 3 waves, we selected 22 items. They span the range of sensitivity, factual, and subjective topics because we really want to see how this mode changes plays across different items that have different features. For our analysis, we divided into 2 parts. The first part is for us to estimate the differential mode effect. So this is a simple analysis that we are comparing the estimates for the mixed mode versus the estimates for in-person mode. So this analysis only used data from wave 5. In addition to that, we used the Markov-latent class analysis and decomposed the differential mode effect. Then we wanted to see how different error components actually are playing in this mode effect that we are seeing. So those are the two parts for the analysis. Sorry, I don't know. Okay. For this analysis, we selected 22 items, but in this presentation, I'm only going to use 10 items to demonstrate the results. The 10 items are good health, which is asking, how is your health? Are you in good health? Insurance is having the insurance or not. Dental is in the past 12 months, did you have you had a dental examination? Blue means ever felt blue, and sad means ever felt sad in the past 7 days. Intercourse is asking, have you ever had vagina intercourse? And this is attention to female, attracted to female and attracted to male. Cigarette use for the past 30 days. And in the past 12 months, have you had seriously thought about committing suicide? As you can see from those items, some of them are more like factual, like for example, having insurance, but some of them can be very sensitive, like intercourse or sexual preference or suicidal thoughts. So there are different items here that we are examining. For the part 1 analysis, basically, we're just comparing the estimates between the mixed mode and the in-person sample. As you can see that because when we selected the sample, the mixed mode sample and in-person sample, sample 2B, are actually a random sample from the same population because we selected those samples randomly from the entire sample. So they should agree with each other if there is no mode effect. So the magnitude of the DME can really be used as an indicator of the magnitude of the existence of non-sampling errors that can vary by different mode. Because different estimates have different effect size to increase the accuracy to estimate the mode effect, we're using the relative DME, which is using the DME divided by the mean of the 4-wave 5 sample. So which means we combine the sample the mixed mode sample and sample 2B together in order to estimate the full sample estimates. So this is a chart showing the relative DME across the 10 items as I discussed before. And we also did some hypothesis testing. The first hypothesis testing is checking to see if the RDME is equal to 0. The second is to see if it's smaller than 0.5, and the last one is checking to see if it's less than 0.1. What we found is that the absolute RDME significantly exceed 10% for only 2 items, which is blue and sad, and significantly exceed 0 for one of the items, which is intercourse. We're not surprised to see the results because these items are more subjective, and especially for sad and the blue, because from the survey literature, there's always some discussion about people who have depression or being emotional. It's harder for them to participate in-person interviews. That's why from the web and the mail mode, we are actually seeing a higher prevalence of feeling sad and blue than from the in-person mode. That's why the RMDE is positive. And for some of the estimates, some of the RDME you can see are negative. So for example, for the intercourse, it's actually the prevalence from the mail and web is lower than the estimates from the in-person interviews. Even when we found those significant DME, we don't know which mode actually is better. So this is so this information can just help us to see, okay, there are some mode effects, but actually which mode is better? What are the aspects from the survey that can cause these differences? So that's why we are using the Markov latent class analysis in order to do it. So MLCA is a model-based approach for estimating the measurement error parameters in longitudinal categorical data in particular. The measurement error in a sample proportion is a function of misclassification probabilities associated with the measurement process. So for example, someone ever felt sad. Well, is that a true positive, which means that this person truly felt sad, or it could be a false negative, a false positive. So there are a lot of different metrics that we can use to estimate misclassification probabilities. From our results, we use the 3 different metrics. The first one is specificity, which is indicating the true negative rate, and the sensitivity, that's reflecting the true positive rate. And last, we're using accuracy to kind of summarize the true negative and the true positive rate to examine the probability the survey response agrees with our individual's true classification. So when we are discussing about Markov latent class analysis, there are always a path diagram. So here is our diagram for the model that we're doing for this analysis. As you can see here, let me just use field SAD as a variable here. So the Y actually is the variable that we collected from different wave. So Y3 is a person who reported they felt sad or not in wave 3, and Y4 is in the response in wave 4, and Y5 is the response in wave 5. What we are trying to model, trying to predict is the X value, which is the latent construct at different waves, which you can consider it as the true value. So what we believe is that for this model, X3, which is a true value, and also the mode of data collection is affecting the response value, Y value, which is what we are seeing from the data. What is also affecting the response is what we call the joint effect of the sample and the mode. So for example, for the mixed sample phase 1, it could be a sample 1 and the mode equals to 1, which is mixed mode. And also for the mixed mode sample, we had a NERF phase, which is the second phase, what we did the in-person interview for these cases. So you can see,
10 minutes.
okay, yeah. All right, so you can see that in this diagram, basically what we're trying to model is to see how X3 and M3 is affecting the Y3, or from other waves as well. For the dashed line is assuming that across different waves, the association between X and Y is the same across different waves. So this is the structure of our model. From our results, the first chart is showing the sensitivity results when examining different items. What you can see is that for a lot of items, their sensitivity rate is close to 100. So which means that the AdHealth survey really is measuring our latent construct X. So the Y and X are meeting very closely together. There are some items that have much lower sensitivity, which means that they have larger errors. So like blue and sad and suicide thoughts, those are the ones that is a little bit problematic. As you can see, the dark blue line bar is actually higher than the light blue bar, which means that the in-person, the web and mail sensitivities is higher than the in-person sensitivity, actually indicating that the mail web mode is better than the in-person mode in terms of sensitivity. So this is corresponding to what Brian mentioned before, that in the literatures, usually we believe that in-person interviews results better quality of their responses. However, from this mode effect, we are actually seeing that sometimes the mixed mode actually is performing better. The second chart is showing the specificity from these results. And as you can see that for most of their items, the two modes have very similar results. There are items for good health and insurance and dental. Those actually have very low specificity, but the two modes almost have the same rates. Another thing to note is that the light blue bar usually is higher than the dark blue bar, which means that the in-person interviews result slightly better results in terms of the specificity. And at last, when we are examining the accuracy, we can see that the two different modes actually have very similar accuracy rates as well. Although for some items, their accuracy rates is a little bit lower than 80%, but overall, they're very good. So for the latent class analysis, we also compute the bias of the weighted mean estimates for samples for the mixed mode 2B and compared it with the 4-wave 5 sample. In this case, the total bias was estimated from the latent class method as the sum of the measurement error bias and the non-response bias. To decompose the total bias, we can separate it as the measurement bias and non-response bias. For the measurement bias for the sample, we estimated it as just using the wave 5 sample. We compare the weighted sample mean based on the Y values minus the weighted sample mean based on the X values. So this is the measurement bias. And for non-response bias, then we compared the X weighted estimates of the X values among the wave 5. So this is for the mixed mode sample, and then compared it with the 4 sample, or the X values for the sample 2B, then divided by the 4 sample in order to study the non-response bias.
5 minutes.
Then, okay, perfect. And so what you can see here is we are showing for different items, we are showing the relative measurement bias for both mixed mode and in-person mode, and also relative non-response bias for the mixed mode and in-person mode. Okay, so here, let's just see what are the significant biases that we are seeing from this chart. The most outstanding errors you are seeing here probably is the purple bar, which is the relative measurement bias for the in-person interviews. As you can see that the measurement bias for in-person interviews actually are higher than the mixed mode in general. And for non-response bias, also, the green bar is much higher than the blue bar, as you can see from the chart, which means that the relative non-response bias from the in-person sample is also higher than the relative non-response bias for the mixed mode. At last, if we just look at the relative residues for the mean squared errors, then you can see that for the new design, which is a dark blue bar, is lower than the light blue bar for most of the items, except for SAD and just a few other things. In summary, the motivation for us to transition from the in-person interviews to mixed mode data collection at wave 5 is because of funding reductions also. We wanted to, the data collection costs per cases is increasing if we are continuing doing the in-person interviews. For the mode effect analysis, we used the parallel sample 2B in wave 5 in order to estimate the mode change, how the mode changes will affect the survey response. And in this analysis, we used the data from 3 different waves, and we selected a total of 22 items in order to estimate how the mode changes will affect the estimates for those items. We did 2 different analyses. The first one is simply to compare the estimates between different samples collected from different modes. And the second part of the analysis is trying to decompose that mode effect by using the Markov latent class analysis. The bad news from our analysis really is that the risk of mode effects when comparing wave 5 with the prior wave estimates is relatively high. As we found from those 22 items, 8 items actually are significantly larger than 0, and 4 are significantly larger than 10%. So there are some mode effects when we are comparing estimates from wave 5 with the prior waves. The good news actually is what we found from several important respects, that the new 2-phased mixed mode design actually outperformed the traditional designs with greater measurement accuracy, and reduced the residues from the non-response bias, and also result a substantial reduction in the total MSE of the estimates. And I provided some more detailed results below. For the future research in wave 6, we plan to continue to include a parallel benchmark sample, featuring the in-person interviewing, and continue the mode effect analysis. Because in our current mode effect analysis, we only studied the 22 items from 3 different waves. We're considering repeating this analysis for a wider selection of items from AdHealth, and we will try to use all 5 waves to test the validity of the key assumptions, and to verify if our current findings can be also found from this new analysis. The results from the latent class can also be used to assess the measurement errors of survey questionnaires in terms of sensitivity, specificity, and accuracy. So as Brian mentioned, that we have published our method in a book chapter. So the researchers are can also use this method to assess the mode effects from different waves as well. So that's it. Thank you.